How many in the audience have had anything to do with tunnels? I just want. Oh, good. Sometimes it's 2, 3. That's great because, and don't hesitate to ask questions if you want to. I'm happy to be interrupted if I go too fast, which is my tendency, right, Ross? Yeah. Is this up a little bit? Oh, a little higher. Okay. The SR is State Route 99 bored tunnel project is what I'd like to talk about today. It's in Seattle, Washington. It's a highway tunnel under the city. It's notable for a couple reasons. At the time of bid and time of machine order, it was the largest TBM ever made, 17.5 meter diameter. And it's still one of the largest machines around, particularly in North America. It was ordered in 2011. It's a defining case history to me because it set a new standard for what you can do in terms of ground control, in terms of literally controlling the amount of ground relaxation or ground loss that occurs when you tunnel. And the credit goes to people I will call out later. It isn't the board of consultants. It's the people who actually did the work. My presentation is going to be from the owner's perspective because I worked for the owner for over 10 years on this job, longer than I wanted to, but that's the way it turned out. A little bit about the background. I'd like to talk about the design approach, contracting approach, because it was important, RFP approach or evaluation, which is difficult, TBM issues, manufacturing issues, startup, shutdown, breakdown, tiers, governor stepping in, stop work order from the governor, restart, and then what I'm hoping to focus on, if I don't run over too badly, is the actual results from mining under Seattle. I'm happy to have this recorded today because people who are interested, you can look at these plots. There's a lot of detail in the plots, and I'm certainly not going to do a point-by-point presentation. I promise I won't do a point-by-point presentation on the plots, but there is a lot of data. It's good data, and I think it's, for those who are interested, it's worth looking at because this is what taught me what you need to do in order to be successful. And then there's the court case. There's always the court case. Just finished up last fall. Here's the technical review board, picture of us and my colleagues for WSDOT is the Washington State Department of Transportation. We were the board from 2010 to 2017. A lot of you know Rick Lovett. He was a TBM manufacturer. He was a great asset. Brenda Boki is a geotechnical engineer, project manager with PB, Parsons Brinkerhoff. She was on her own at the time, and she was our coordinator with the WSDOT, with the management. And Toby Whiteman, others probably you know also, he's on some boards here in Canada. Great construction guy, done a lot of construction work. Project was basically to replace an aging viaduct that I was frightened to even walk under. It was constructed in 1950, double-decker viaduct. It was damaged severely by the Nisqually earthquake. Here's a picture. I gotta learn how to work this thing. You can tell how old I am. This is the viaduct right there, this ugly structure. It literally divided the city of Seattle from the waterfront area. And if you've ever been in Seattle when that thing was running, you could hardly hear yourself think when you walked in. It was awful. And it's gone. It was the greatest improvement ever for the city of Seattle. It was badly damaged, had concrete falling off it. And I literally, when I would walk from downtown to get dinner down at the seafront, I would run under the thing because it was just looked unstable just to look at it. This is the old viaduct here, and the new tunnel started here at the south end where the stadiums are. It's about 2 miles long and goes all the way to the north end where it connects with the I-5 freeway. This is the tunnel. It goes right under the city of Seattle. It was 2 miles long. Here's a plan that shows the zone of influence in terms of the buildings on the surface that were impacted by this tunnel, and a geologic section showing a profile showing the depth of the tunnel under the buildings. Roughly 300 buildings were affected, potentially affected by what we call a zone of influence. All these buildings had prisms on them. They had the Cyclops instrumentation, monitoring. We had MPBXs, multiple position borehole extensometers, with piezometers at the bottom every 15 meters, wherever the whole alignment. We wanted to watch this thing very, very carefully. And it turned out to gave us a huge amount of data, and it was worth every penny. The tunnel starts in the south end. This green block right here is called Safe Haven 3. That was our last point to do something before we sort of let the machine go, head under the viaduct, which was going to fall down if you looked at it wrong, and then head across the city. The geology is, you guys probably know the geology because it's very similar to up here. It's glacial. The tunnel is completely in glacial soils. The blue is over-consolidated clays. The purple is till. The tan is till-like, which means the geologist doesn't know what it is. And the orange is outwash deposits. The majority of this bore was in cohesionless material or mixed face. Or mixed face conditions. The design approach, or the contractor approach, was design build. We basically had reference documents that were sent out, conceptual design. The contractor could then finish the design as a design build. We was given 5 months to prepare a proposal. He was given a stipend, as I recall, $4 million, something like that. And what was interesting about this job is it had what was called alternative technical concepts allowed. In other words, the contractor could bid an alternative to what you had proposed, provided it didn't violate WSDOT's design manual. And you had to get pre-approval by WSDOT before you could submit it with your bid. And then you could include it in your bid and price it and have it evaluated in the best value approach. It was actually tricky, it was complicated, but it actually turned out to work very well. The selection was based on best value, price, plus technical merit. There were 4 SOQs, 2 submitted, 1 EPB, 1 slurry. The RFP evaluation was, like I said, best value scoring. Turned out we had an upset price of about $1.2 billion. Both bidders came within a million of that upset price. So the evaluation turned out to be totally technical merit because there was no difference in price. And anyone who's done best value evaluation knows it's not easy. It's never straightforward. There's always the good with the bad. You look at the proposal, there's some really terrific things, and then there's some things you wish you didn't have to see, or you try to ignore it because it doesn't look so, you think the guy shouldn't be doing this. What really won this job for Dragados, the Spanish tunnel contractor, and Tudor Perini was their innovative approach to startup. And I'll show you that in a minute. They also had a very innovative pressure control system called a KEEP system for controlling the face and shield pressures. Not so good things in the proposal. An EPB machine, earth pressure balance machine with a ribbon conveyor, a deep cutter head for free air changes on an EPB machine. Hadn't been done more than once before. Face pressure below hydrostatic on one of their plots, which made you sort of wince when you saw it, in cohesionless material no less, and volume loss of 0.5% assumed that would not meet the settlement criteria. If you used 0.5% volume loss, you would not meet your settlement criteria. So you take the good with the bad, the way it is. These guys won. This is the winning approach here. and it's pretty amazing. They put secant piles for 1,500 feet on both sides of this machine. And they had a buoyancy slab for the first 500 feet of this drive and tied it down to the secants. And these secants are huge. They're 10-foot, 3-meter diameter secants, over 100 foot deep. You know, just one after another. They had Malcolm down there just going like crazy day and night. The beauty of this proposal was they could start much sooner at lower depth of cover than what we had planned. We were going to use a much deeper box with all the problems to get started. Here they could start with a half a diameter cover because they had a buoyancy slab. This is I'm sorry, I'll show you. This is the buoyancy slab here, right here. The other real advantage of this 1,500 foot protected drive is this protected the viaduct. They could almost do anything they want in here, and they did. I'll show you later. And protect the viaduct, protect Pioneer Square, the old buildings, and protect the waterfront down here. So this was an incredibly long test section. Yeah.
I'm not familiar with buoyancy slabs. How does that work? Or what's the concept?
Buoyancy slab, the problem is the tunnel boring machine is this big void. I mean, it has a lot of weight, but actually it's buoyant. It will float, and what's worse is the segments are, you know, you basically have a tunnel which is filled with air, even though there's a lot of weight with the segments. Everything will float out of the ground because of the water table being so high. The segments, not so much the machine, but the segment part, the tunnel itself would literally float out of the ground if you didn't hold it down, just by buoyancy, by the volume, the 17.5 meter cut with a 2 foot thick segment was not heavy enough to overcome the weight, the uplift from the water. So buoyancy slab literally is tied to the top of this slab is literally tied to the secants. So the secants are providing a tension, uplift against uplift. So the machine and the tunnel literally, they dewatered here at first so we could break in. But when we turned the dewatering off, the tunnel would have wanted to pop right out of the ground like a bathtub, like a boat. But this gave them 500 more feet of tunnel, and then they didn't have to dig so deep for the U-walls that they put in, the slurry walls they put in for the startup. But 1,500 feet to Safe Haven 3 was a terrific idea because, heck, who couldn't learn to run a tunnel boring machine at 1,500 feet, right? This is the EPB machine. For those of you familiar with tunnel boring machines, it looks like an EPB machine. It's got a screw conveyor, double auger, ribbon. The difference is it's huge. It's 17.5 meter diameter. The auger, this auger here, which takes the muck out by a turning screw, was 1.5 meters in diameter. It was monstrous pipe, and it has a hole in it, what's called the ribbon. I'll show you in a minute. That was 3/4 of a meter thick. The really unique thing about this machine is this cutter head. This cutter head here. Here's a picture of the cutter head, a sliced section. Each one of these spokes on the cutter head is open and connects to a central section here where you can walk in from outside the machine. You can walk in back here, go in here, go up the spokes, and change out any cutter you want in free air without depressurizing the face. It's great. It's a great idea. It was invented for slurry machines. Slurry machines have very low density, extremely low density, so the muck will flow right through them very easily. EPB machines have much higher density muck that's conditioned in muck, and we were very worried that a 5-foot deep head would never work. It would block. It would just block up unless you really watered up the muck and used a lot of foam, used a lot of water to make it flow. So this cutter head Hitachi Zosen told us they had done this before on a 6-meter machine, although I never saw the results. I never actually saw it. So this is really the first time they had done this, as far as I'm concerned. And it may be the last time. But this was a big concern to Rick Lovett and others. How are you going to make the muck flow through that head? And, you know, basically control it as it comes up this auger here. The really nice feature they had that's called this keep system. It's a system where they have bentonite prepared on the surface. They pump it and pipe it to the tunnel face. They have tanks down below. And this system can be used to pressurize the face or the shield while you're mining or while you're stopped. And you can set the pressures wherever you want, and what it prevents is a depressurization and a ground collapse. And it worked beautifully. Actually, it worked very well. This keep system is something that we now want to specify on all machines of this type, but because it allows you to not accidentally depressurize. So you have a long weekend, it holds the pressure constant. It keeps pumping the bentonite in, just pumps it in wherever it's needed. You just set the pressure. They call their name is Keep System. Dragados calls it Keep. Incidentally, I should tell you that Seattle Tunnel Partners is the joint venture name. That was Dragados and Tudor Perini. The one criticism or issue with its bentonite system is the bentonite was prepared on the surface and pumped, so they were limited in the density of the bentonite they could pump. The density was 1.08, 1.07, which is pretty low for a slurry machine. So if you have a porous ground, or a coarse ground, it's going to flow away, and it did. But it worked, but not. I'm just saying that it would be better if you could have a higher density. But this system did work, and actually worked very well. Here is again the problem that I mentioned earlier. This machine has a 5-foot deep cutter head. The muck has to be conditioned up here at the face, travel through the head, go into the plenum here, get mixed up, and then is extracted via the conveyor here. This ribbon conveyor, which is like a corkscrew. Theoretically, the maximum pressure is 7 bars at invert. It's supposed to be dropped uniformly along the auger length to the tail where it's dumped on a conveyor uniformly per turn of the ribbon. This design of this ribbon was 30 flights or 30 turns to drop 7 bars. Is 0.23 bar per turn. Mitsubishi, who invented this, here's their design parameters. Ribbon, 0.1 bar per turn. Archimedes, full flight screw, 0.2 bar per turn. Guess what? It's not going to work. And the worst part of it is we have to make this muck super wet to get through the cutter head. So how are you going to drop that head through this in this uniform way without some sort of a blowout? So you had these two problems. You needed to have a very fluid muck to get through the head, well conditioned. You needed a thicker muck, higher density, to drop the pressure uniformly and not have it blow through. Another way, this section is a ribbon conveyor picture. This is the way those ribbons or the flights turn at a certain RPM and extract the muck at a certain rate. And the center core is wide open. That was at 0.75, it's 1.5 meters, 0.75 meter. It's a pipe. It's nothing more than a pipe. It goes all the way down to the invert of the tunnel and comes all the way out to the belt. If the velocity of the material, if it starts to blow through the center, and the velocity of the material coming through the center exceeds the rate of your extraction on your ribbon, you lost control. You have absolutely lost control. You no longer have muck balance. You have to slam the rear gates to try to get control back. And that's what really concerned us. This is the wrong, and the reason they did this is because of the boulders. They thought there was going to be a lot of boulders. The ribbon conveyor is for transporting boulders. And admittedly, the GBR, the baseline report, said that there was going to be quite a few boulders. Although there's other ways to deal with boulders. One is cut them up. don't try to take the whole boulder out in one bite. Thank God this machine had 2 rear dual gates at the end. These are slide gates. They're massive gates. They're about 4 inches thick. Steel plate. They literally slam shut. They had 2 of them about 1 meter apart, and they turned out to be crucial to running this machine later on. This is the settlement criteria the contractor said he said his volume loss as he excavated, he was going to lose 0.5% of the ground. Well, if you do a calculation, and the spec was 25 millimeters. At the surface, 25 millimeters of settlement. Except at Pioneer Square, it was down to 13 millimeters for a section where we went under some old buildings. So if you take the 0.5% volume loss, you transfer it up by the cone, the usual, and look at the trough, you find it doesn't work. You're at the either end where you're shallow, it wasn't going to work. You're going to be double the amount of settlement allowed. So that was another issue that we sort of pointed out to them, that it's not quite going to work. TBM was manufactured in Japan, and like all big machines, they do bench tests. Once the machine is built, you take it out and they run it. And there's big celebration, sake, and everybody goes out there and they do the whole ceremony. Well, they turn the head, and next thing you know, pieces are flying off. I mean, they literally, I'm not exactly sure why. Rick Lovett told me it was all tolerances. The tolerances were not sufficient. The main bearing seal. This is the TBM at the factory. This is what's called the main bearing seal. This is you have a turning head. You got to seal it from the bearing, the bowl gear, all the components. You have to seal the high pressure water and muck from all the other components. And this seal, for the cutter head to the main structure, is a bunch of rubber seals, cascaded seals that work at different pressures. They have retaining rings. These are the rubber seals with retainers. When they were testing it, they lost tolerance and ripped them all out. Apparently someone heard sound of metal, and I guess they stopped the sake and all that stuff. And sure enough, they took it apart. They had to take the whole cutter head off, disassemble the whole machine, and they found this. Well, it took them 3 months. They redesigned it, changed the tolerances, redesigned the seals, put it all back together again, and got it on the boat. Startup occurred. It delayed them about 3 months, and they did ship it not fully assembled. They didn't have the locks in place. They didn't test the conditioning systems. They were so rushed. We had such an accelerated schedule that they really left some things undone. They really did. And I must admit, I probably didn't mention it I passed over at my slide. We gave bonus points, I should say WSDOT gave bonus points if you gave a better schedule, an accelerated schedule. I don't think it's a good idea to ask the contractor, can I go faster? Sure, and I'll give you bonus points on when I evaluate you. Well, that's what happened. He said, I can build this machine in no time. Yeah, I've never built one before, but I can do it really quick. Anyway, a month later, they got the machine out, put it together, here it is in the slurry wall section, and ready to go. It started up about July 2013. And a lot of every project has difficult startups. This one was no different. Because they didn't have everything in place, they didn't have the locks and whatnot, and they decided not to put a launch seal. It's a rubber seal that you put around the perimeter, so when you break out the wall, you can actually condition the muck and build some pressure so that you can extract the muck. Though they decided we don't need a launch seal. So when they started mining through this concrete wall to break out, guess where all the muck goes, right? There it is. It just poured out all over the floor. And then they had to dump water in because you have to cool the head. I mean, it's hot when you're cutting. With these disc cutters, you're trying to cut concrete, like 5,000 PSI, whatever MPa, 5,000 PSI concrete. Well, guess what happened? It rehydrated in the head and blocked the whole cutter head. So they had to go in there, chip it out, and I go, it's not a great start, but all right, it's okay. So it did clog the head, and that was the first blockage. When they didn't even break out of the shaft, out of the startup area without blocking the head. Again, because of inadequate conditioning and failure to put on launch seal. This is one way to look at what's happening inside what's called the plenum chamber, which is the area right behind the cutter head. You look at the gradients. You have these earth pressure cells. These are earth pressure cells. There's 12 of them in this side, this cutter head. These are the two top ones, 2 over here at spring line, 2 at the bottom. So there's in between ones, but there are 12. If you look at the pressure differences between these cells, you can calculate the density of the mug in that back side of the cutter head. And we did this just to sort of see how he's doing with conditioning muck. One of the critical things with EPB is getting a nice conditioned muck that'll flow nicely, hang together, won't segregate. So we looked at this quite frequently, and in situ density is 2.1 tons per meter cubed. That's the colors, this orange color and red. This machine, typical EPB density is 1.5, 1.7 ton per meter, the green and the blue. This machine, the density of the material in back of the cutter head, after it had been supposedly conditioned, was ready to be extracted, was in a lot of times near in situ density. Incredibly dense. It was literally what it said to us is that cutter head is blocked. They were using horrific forces. The forces were way up. Even though we were only 1 bar of pressure, they were cramped. They were pushing that head like they had 5 bars of pressure. And what this also shows is that there's no uniformity. You've got a bit of green over here, low dense, lower, high, it's in situ density over here. No uniformity. And these are ring numbers. These are ring 170 through 177. These are each ring, the average density. And this is definitely something we weren't happy to see. But here's one of the problems that occurred is when you drive a tunnel boring machine like this with a block cutter head, it actually gives good ground performance. Because if you have a blocked head, you don't take much extra ground in. So that all the instruments on the surface that we've installed a ton of extensometers on the surface, they were showing very little settlement. And so the contractor's geotechnical engineer was saying, what's the problem, guys? It's not settling. Get out, go away. But we're seeing this, and we're going, well, how far can you drive with a blocked head like this before something bad happens? And I go, that's not your problem. That's go away. Well, it didn't take long. 1,000 feet down, this 1,500-foot section, thank goodness it was still in the secant section, the protected section. They managed to cram the head so full of cohesionless material that they couldn't move. They literally, it was at ring 149, I looked at the density in there, it was 2 tons per meter cubed, the average density of the material crammed into the plane. And they were trying to move forward, and they couldn't move forward. What happened is that earlier on they were in a combination of cohesionless material and clay. And the conditioning, by adding water, they got a pretty good mix, and they were able to mine. Plus the head was only about 1 bar at the crown. And it was working, sort of. And then they started to break into ground, which was almost more and more cohesion material. And the head was building, because we're going down grade. The head was going up. So they were the material started to segregate on them. They were losing too much ground, so they slammed the rear gates. You know, they closed their double back gates. And they opened them that much. Out of 1.5 meter, they'd open them that much. Well, how much, you know, how far can you drive forward before you cram so much material in there? You're stuck. And that's exactly what happened. They literally plugged the head. Well, not wanting to waste time and go out again and dig all the muck out of the cutter head, they decided, Brigados made the decision as management, top management decision, to push the machine as hard as possible to push the plugs of material out, try to force it out. I mean, I've read some story. I wasn't there, but I read stories about guys who were there and what was happening. It must have been a fair amount of shouting going on, particularly by the Japanese who were there. They literally turned off all the safe sets, everything, every interlock, everything that they could find to turn off, and they put the pedal to the metal. And guess what? They blew up the main bearing seal. So that's it. Now, just before they blew out the main bearing seals, they hit this pipe here, this 8-inch diameter, 3/8 wall casing. This took all the blame for this was the piece of steel that destroyed Bertha. That was the name of the tunnel boring machine. And this is the piece that got thrown up on the surface. I'm glad I wasn't up there, but that night, and then these pieces on the pallet over here are parts of the casing that got eaten by the machine, came out. And then we also hit 2 big boulders. These are pieces of the boulders. So this was 11 rings or 22 meters before they blocked the head. We hit that casing. And that casing became the culprit for the machine, why the machine broke. First, everybody was laughing about it, but then it became serious when all the lawyers showed up. We often wondered why they went to such an extreme of pushing the machine to the point where it broke. And I think one factor was the machine was guaranteed for 200 rings, 1,300 feet. So I do think it influenced the guys running the machine to say, well, I'm at ring 149, I got 50 more to go. If it breaks, it's not my, he's going to fix it anyway. So that was one factor. So, all right, the only way to fix this thing, obviously, is 17.5 meter machine is put in a rescue shaft. We were so fortunate to still be in the secant section. So we could build a rescue shaft using the secants that were already there by just completing the shaft. They put in a cutoff section back here. But we built the walls about 100 and some odd feet, a little over 100 feet, 120 feet deep. Dewatered this section, dewatered the base, and the machine would still turn. And after they cleaned the head and cleared it with spaders, I mean, they're in there with spaders and jackhammers. After they got it cleaned out, they mined forward. And here's the machine coming into the rescue shaft. Look how hot it's getting. It's blowing off all the water. The steam is coming off. Here's the machine in the rescue shaft. We had to cut the front shield off, cut the intermediate shield, cut these shields off, remove them, and pull the head. That's a 2,200 ton pick. French company did it. It took 2 years to get the machine, to build the shaft, get it in the tunnel, bring it up, remanufacture, take it all apart, remanufacture the main bearing seal, bring in a new one from Japan. They machined it on the surface in their tents in the winter, put it all back together, drop it back down, and go on. It took 2 years almost to the day, 2 years roughly. The machine was relaunched out of the shaft on the 4th, 2016, 2 years later. Good news is the main bearings seals, the redesigned system with new tolerances, where all the displacements were monitored by lots of instrumentation. They had track seal instrumentation, displacement instrumentation, all over this seal, all over the cutter head area. And it was 100% working fine. Bad news is they got a sinkhole right away. There's right here is the rescue shaft. Here's 80 feet forward, big sinkhole. Kind of disappointing. We have this sinkhole. Basically, here's a picture of the geology where the sinkhole occurred. It's in cohesionless outwash deposits, about a diameter down. This is pretty loose material up here, recent alluvium, and here's the till. It took about 100 hours for that over excavation to prop to the surface. The machine had advanced about 100 feet ahead before it came to the surface, and we noticed it. About 250 cubic yards lost. And the next day, Governor Inslee shuts the job down. It was the best day of my life. I'm so happy he shut this job. He really made my day. I think I was up in the Sierra somewhere when I read about it. I was extremely elated. This saved the board from having to do a very nasty job writing reports saying we cannot approve this machine mining under Seattle. We didn't have to do that because the newspaper was doing it for us. Seattle Times, sinkhole worries loom large as Bertha prepares to dive under viaduct downtown. I mean, that's mild compared to what was really going on in the owner's camp. There was no way that we could let this sort of sinkhole situation happen under the high rises of Seattle or the viaduct. It was just not. So here's the situation we were facing, and here's the rescue shaft, here's the sinkhole. The machine had mined to about here, 100 feet ahead, and this was the end of our test section. I mean, we were running out of test section. We had 1,500 feet to learn how to run this thing, and we're down to less than 300 feet left. And we basically had run out of options at this point. I mean, we were supposed to be up and running. And look at the grade of this thing. We're going down pretty steep, and the pressure is going to be building up, so control is going to get harder and harder and harder as we get into cohesion materials and higher pressure. If you can't run the machine right here, how can you run it right under the viaduct? This is the viaduct. This is what we were going to do. We were going to mine within 15 feet of the base of the tip of the piles on this old structure. And this is basically end-bearing piles because this material here is fill and relatively loose alluvium. This is the till. So these are, for all practical purposes, they're end-bearing piles, and we're going 15 feet from it. How much settlement could we allow? It's just virtually nothing. And this structure is already damaged. It's fallen apart by itself. It's just, it's all cracked, and it doesn't have any capacity left for additional settlements. So there was a 5-week shutdown. During the 5 weeks, the governor asked to meet with the board, the technical review board, and we had multiple meetings with the board. He asked us, quite frankly, what the problems were, what we thought what should be done, and believe it or not, changes were made, and a conditional restart was allowed after 5 weeks. And here's the changes that were made, the proposed changes, and they were instituted. First thing was we had to get a new management team. Basically had to change the upper management at Dragados in order to get people who really understood and appreciated the problems. two fellas, actually it was four, came over. There was a project in UK called Crossrail, where they had an EPB machine running, just finished up. Four guys, two of them, two upper management, came over. We met with them, had dinner with them, and found out right away they're brilliant. These guys knows what they were answering our questions before we asked them. They knew what to do. They proposed, these two guys, to modify the machine. We put in what's called plenum air release system. They were going to change their whole approach to conditioning. They brought on 3 consultants from Europe, additional one from Condit, 2 from old guys from who used to work for Heron Connect. And they basically told us how they were going to approach modifying this machine to make it work. And Rick and I were just terribly impressed with these guys. In terms of TBM operations, they were going to go into a strict protocol where every morning we review what happened the day before in terms of the parameters, look at all the ground monitoring, and then set today's parameters. So every morning at 7 a.m. there was a meeting at the contractor's office to set all the parameters for that day and review previous operational parameters. And it was a joint effort between the contractor and the owner. So now how do you make this machine work? It's sort of theory versus practice. The theory was you're going to use the red line to drop the pressure, right? You're going to drop the head from 7 bars, you're going to go down to nothing by the rear gate and pop. It wasn't going to ever work. That's what they proposed. To make this thing work, they're going to take this EPB and turn it into a slurry machine. That's basically what they did. They changed the density. They conditioned so much in front that the material was basically a slurry density, about 1.1 ton per meter squared. They conditioned it with so much foam and so much water that the material would flow right through the 5-foot cutter head, no problem. That issue went away. Now how do you drop the head? You got thick water coming up this pipe. They're going to use the rear gates. In a very coordinated way, they were going to use the rear gates to drop the head. They're going to drop 4 bars head at the rear gate. But how do you do that if the material segregates on you? And what'll happen is the water will come out and you'll just trap all the larger particles and it'll just segregate everything. The way they controlled that, and it was brilliant, is they injected polymer here, huge amounts of polymer. And the polymer binds the water with the muck, with the sand, to the point where it looks like a homogeneous product. It looks like conditioned muck. I would watch it on the conveyor belt, and it looked perfect. It looked absolutely perfect. There was no segregation of water and muck at all. It cost a fortune, but it worked. So they had figured out a way to do this. They also installed a bleed port up at the top. We wanted to make sure we always had the plenum chamber filled, no air. They put in a pressure cell so we could see what's happening up there, and a port, and then dumped back on the conveyor belt back here. And it automatically would purge during mining. To make sure you always want to fill that cutter. You don't want to have air at the top of that cutter head ever. One thing we did look at was we knew that this material, this ground, was very, very permeable. And I did some simple little fits of, if you look ahead of the cutter head, ahead of the tunnel boring machine face, the blue line here is the pore pressure, excess pore pressure. This is above hydrostatic, the blue lines. These are measured by the piezometers every 15 meters. We had excess pore pressure 400 feet ahead of us. We could see the machine coming 400 feet by just looking at a piezometer. You wouldn't see it on the extensometer, but we were losing slurry way ahead of us. This ground is so permeable. If you fit a Tice solution best fit, you get 3 to 6 centimeter per second permeability. I mean, we were losing slurry. I knew it. We knew we were going to lose slurry. So if you know that, you have a couple of models you can use for figuring out what sort of pressures you should run at. One is called the membrane model, where all the pressure acts on a membrane, a cake, a filter cake. So 100% of the face pressure works on the soil. That's not our case. This is our case. there's penetration. The slurry is penetrating, and we get excess pore pressure ahead of us. The penetration model is what we had to use to evaluate it. About the time we started up, I went to the conference, the World Tunneling Conference in San Diego, I think it was, and these guys from Ghent University gave a paper on phase equilibrium and permeable ground. And they have a little simple program, you can get it, in the paper, and it basically, they simulate the flow of slurry from the tunnel face with radial flow using point sources. Ask Ross if you want more details. Here are the curves that they project. They showed some curves of comparing the data with their actual model. Their model is the dotted lines and the other, so what it really demonstrated, this model demonstrated that they had a model which you could use for estimating face pressure to have a stable face in a permeable ground that we could use. And I gave the model to the contractor, and I ran it myself too. I said, here, you guys, use this. It worked. It's good. It's good for you. So, mining under Seattle, they started up. We gained considerable confidence in that very short section of 300 feet. These guys demonstrated to us that they actually, after they made the modification, that these guys were going to take charge, and they knew what they were doing. They were really, it was like day and night. It really was. I'll give you the results right off the bat. When we mined under the city, the maximum settlement at the surface, remember the spec number that they were allowable was 25 millimeters max. We got 2.5 max, 1/10. And we had an allowable of 2. And that was just at the deepest cover area. It was barely measurable. And that was a very small region where we had very deep cover. Here's just some preliminary data. This is the tunnel this is the south end where we started. That's Safe Haven 3, mined under the city all the way to the end where we broke out at the north. I've got 3 curves showing here. One is called the cover ratio, just to show you how the data, how it varied by depth. The cover ratio is the depth to the crown divided by the diameter. That's this line here. We started out with a cover ratio of about 1.25, where we broke out and went under the viaduct, went up to a max of a 3.5, which is pretty deep, under the deepest part of the city, and then broke out at a half, which is really shallow. Water table was max of about 3.5 bar. That's a crown. So at the bottom, we're dealing with basically 5.5 bar, roughly, at the bottom of the machine. So this is crown. We ran out of the water at the end and came out dry. And this is face pressure, this orange curve right here. What's interesting about this is if you look at typical data for EPB machine or even slurry machine operation, you'll never see pressures that high above the water pressure. The only place they even get close to matching the water head here, the face pressure, is when they're in the full face of clay, where it really is, you aren't even seeing that head on you because it's pretty impermeable. But they ran this machine at roughly a bar to 2 bars above hydrostatic, which is rare, which is unusual. But it has huge benefits. And it really had big benefits at either end of the job. And I'll show you in a minute here. This is a little complicated, but it has a lot to say. What we're looking at is, again, along the tunnel length from start to end, this is the pressures at the face crown, shield crown, tail crown, and this is displacement at the MPBX 1.5 meters or 5 feet above. That's this dotted line. So this is all this is everything at the upper part or crown of the tunnel. What this shows is the settlement in millimeters, there's the scale over here, went from negative. We actually pushed the viaduct up. We actually pushed the viaduct up about 1/8 of an inch when we went under it. Where we had that 14 feet, went up. maximum of 20, say 20 millimeters. This is at 5 feet above. We're only getting 20 millimeters 5 feet above, not the surface 5 feet above. So the surface settlement is roughly, again, a tenth of this number here, as the note says, and then down to a few millimeters at the end. And if you look at the way the machine was run to achieve this, is the face pressure was very high where we had low cover. Here and here we had high face pressures. Here we were running 80% of overburden at face pressure. And then the next pressure back is the shield pressure at even a higher pressure by about a half a bar. They ran it about a half a bar higher than face at crown. That's the orange line here. And then the last pressure kick, so to speak, is the tail. And that was run another half a bar higher. So that's the gray line here. So we ran at very high pressures where we had shallow cover in order to cut the settlements. When you're deep, you don't have to cut the settlements as much. When you're deep here at 3.5, a cover ratio of 3.5, it's not necessary to run at full overburden. Now you're wearing out the machine for nothing. Because you're so deep, the settlement's going to spread and it doesn't matter. And even then, we only got 20 millimeters 5 feet up. It's nothing. And then at this end, same thing. We ran at much higher pressures. This is another way to plot the data. I like this one better because it shows the match of the curves. Here what I've shown is, over here in bars, is the overburden pressure, which is the vertical stress, total, minus EPB crown pressure, minus shield pressure or tail pressure. You can see we're running almost equal within a bar. When we get deep, who cares? Oh, I shouldn't say who cares. That's the wrong statement. I can take that back. I care. When you're deep, we were running 10 bars. There was 10 bars difference between face pressure and overburden. But then it didn't matter. And we only still got 20 millimeters of settlement 5 feet above us. Then when we came out at this end, at the end, again, up go the relative pressures. We're running, again, only 2 bars difference between overburden and the shield face tail. But that ability to control the ground in this fashion was, I hadn't seen this before. I have not seen that ability to control so carefully. So what's the key to doing that other than just pressurizing? The key is fill the gap. You must fill all the gaps around the shield and at the tail. And this is a plot. The only part I want to really look at on this plot is the orange, I guess that's orange color line. This dashed line is the theoretical gap around the shield of the machine from the overcut. It's 3.8 meters. It's actually probably a little less because that's with a new dressing of cutters on gauge. It's probably more like 3.3, 3 point so. And the injected amount, which is this curve here going up and down, was 4.3. They filled the gap plus 12%, roughly. It's probably more like 20%. What it means, they were always filling that gap. They were always keeping that shield around that skin of the machine completely filled with bentonite grout, always. So you had something to pressurize. And it was bentonite, not air. It was bentonite. So that's the shield gap grouting volumes, about 20% over, say. Here's the tail void grouting volume. The tail void is over the segment, and that's the blue line here. Theoretical 24.5 cubic meters per ring. We were getting 5-6% over. This is kind of a magic number, 5-6% over. When I went to Japan in 1995 as a guest of Mitsubishi, that's the number they gave me as their target number to try to get 5% more in the tail. They considered that what to achieve to get good ground control. So here it is again, the same number. 20 years later, exactly the same number. They got that 5-6% over. And you can see the theoretical versus what they're actually injecting. They're filling, always filling. The only area they come close is where you have clay. Probably got some elastic response where it closed, but they're always getting a little bit more in. When we broke out at the end, we were above the water table. And again, very, very porous ground. I mean, very permeable. There's no water, but the slurry, you know, if you're going to pressurize either the gap or the face, the slurry is going to disappear on you. Even if there's no, it's going to even be worse because there's no water there. So we ran the Ghent model, and it's interesting. Here's the water table at the end. It's disappearing, and then it goes away. We're dry at the crown. Here's the cover ratio dropping down to just about nothing. We broke out with half a diameter, which was pretty impressive for such a big guy. And here's the Ghent model results of saying, here's the pressure you should run at above the water table in a very permeable ground. That's the numbers you would get. And here's where they ran. That's the actual phase. They ran above, slightly above, the calculated face pressures. Worked. Around the shield, you always want, again, to keep enough pressure in there so that you overcome any potential for gravity to drop material, you know, to drop any material in. And again, as an example, we had an extensometer number 69 here. And it has a piezometer at the bottom as well as its bottom anchor. And if you look at just a simple free body diagram, total stress, the difference between distance between the shield and the bottom anchor and piezometer is 1.5 meters. So if you know the pressure here, you know the pressure here, and you say it's a 2 ton per meter cube unit weight, or you need 0.3 bar difference. You need 0.3 bar higher here than here to hold it. That's it. It's pretty simple. I like those simple things. Here's the actual recorded data for that as the machine was approaching this piezometer. Initially, before this is dates, and this is basically the TBM was back here. The TBM was mining up to this point here. This is the machine's mining along, and before the machine even gets there, there's 1.5 bar difference between here and here. This is the pore pressure in the piezometer at the bottom, and the green is the shield pressure, and the orange or red is the face pressure. So there's no mining. They start mining, and they're getting closer and closer and closer to getting right under that instrument number 69. And you can see that the excess pore pressure is building and building and building and building. The slurry is actually flowing into the ground and causing an excess pore pressure. It's starting to match, getting close to matching this magic 0.3 bar. It didn't quite get there, but you can see the extensometer, this is the extensometer, is starting to take off now. Right as the machine face comes by, it starts to move. But it's in a controlled fashion, and if you're really imaginative, you can match the spikes with the little takes off of the curve. But anyway, it doesn't become unstable. It's close. I mean, 0.3 is the magic number here, but it's close, but it's working. The keep system is working. It's pumping, it's pumping, it's pumping. They're mining and mining, and the settlement finally settles down after they shut down here. They shut down for the weekend roughly here. The keep system is doing this. It's keeping up the pressures. Then on Monday, they start mining again. And then when they start up, just before, they've got 1 bar difference between the bottom, between the piezometer and the shield. And I get a little more settlement, 13 millimeters. So what does 13 millimeters mean? Is it good or is it bad? One way I like to look at it is as a little check is if you really think this ground is behaving elastically, we should be able to look at it in terms of a you could do a simple hole in a plate type model where the displacement is just the delta pressure between the pressure inside around the shield versus the overburden pressure, radius, and shear modulus. Just hole in a plate, closed form solution. If you take the 13 millimeters and add a little bit, because that's not at the perimeter, it's actually 1.5 meters above, you got an 8-bar delta between the shield pressure and the overburden, a radius of 875. You back out a shear modulus of about 500 MPa, which to me is pretty much like a till or a very dense sand. So it says to me that displacement was basically purely elastic. It's not ground loss in the sense of losing ground. It's closure elastic displacement. This simple little formula can be used for scaling. I mean, Ed Cording has told me he's taken the same, I should say there is a criticism of the data that I've shown you previously. This came from glacial till, which is super strong. Therefore, you can't apply it to my project. I'm in recent alluviums, or like in LA or older alluviums, where the stiffness is 1/3. So, scale it. And if it's 1/3, then the displacement will be 3 times higher. And Ed Cording, he probably read his papers on settlement and stuff, and he said he's tested it, and it works. In LA, where we have much less, I mean, the density, the shear modulus of the grounds is much less, you can get the same result by scaling. It applies. Here in summary, to control ground loss, focus on shield gap. That's basic. If you focus on the shield gaps, both the shield and the tail, everything else falls into place. The pressure gradient, you need to consider the pressure gradient to achieve stability. If you're going to lose the slurry, it'd be better to go with a higher density slurry if you could. That's one thing. And if you do that, muck balance and face stability will follow. Surface settlements were negligible. There was almost nothing. Ground loss as a percent of volume of the face was 0 to 0.1%. And the 0.1% was at that 20 millimeters, 1.5 meters above. The 2 guys that I think who came from Crossrail, Paco Gonzalez, Roger Escoda. Roger's working out in Virginia now on that tunnel job out in Virginia. These are the 2 Dragados guys who came and saved the day. Absolutely. Machine broke out finally, April 2017. It was a big day for everybody, but it was kind of interesting. It was a really big day, but then when you start staring at the cutter head, it sort of went, wow, what in that world is going on here? This is something that has always given me nightmares and others, is the wear on the rim of a cutter head. There was a groove, almost like a machine had gone in there, a lathe, and cut an arc circle around the whole perimeter of the cutter head, and it broke through the spokes. So if we were below water table, we were wet in the tunnel. I mean, there was water pouring in through that cutter head. So when we saw this, I thought, boy, you better pay attention to the rim of your cutter head. You know, I mean, it's hard to see when you're doing maintenance. This is the problem. If you're just changing the cutters and the spokes, you never get out there. And who goes around the rim and looks at the rim? But that rim was gone. The structure was eaten. I mean, we had a very unfortunate incident that cost us 2 years, but we got real lucky right here. Then there's the court case. Now, contractor, as I told you, the contractor claimed the pipe broke Bertha, the machine. Rick Lovett said, it's a toothpick. And there was 2 years of discovery, depositions, went on forever. The claim started at $480 million, went to $660 million, got divided in half because half is going to be paid by WSDOT, the owner, and the other half by the insurance companies because they were going to go after the insurance money for builder's risk. Trial after all the depositions and everything, trial lasted 8 weeks. Rick testified. Jury deliberation, 1 day, less than 1 day. They apparently had an engineer in the jury from Boeing, and he didn't buy any of this. It was a toothpick. It definitely was a toothpick. He didn't buy any of the story that the steel pipe broke the machine. So the jury awarded 0 to the contractor and liquidated damages to the owner. Right? 57 to, I think it went up to 74 million after. Yeah. Then there was the trial for the insurance half, the other half, which apparently just finished last fall. 0 to the contractor, defective design. Thank you.